Hi everybody, and welcome to part 2 of our prime factors, GCFs and LCMs video. Today we're going to focus on problems, and don't worry, it's not as long. I know that was kind of a beast, that last one. Alright, our first example. Two ribbons are 24 centimeters and 42 centimeters long. Each ribbon is to be cut into equal pieces, and all pieces must have the same length, that is a whole number of centimeters. What is the greatest possible length of each piece if there is to be no wasted ribbon in the end? Now I know that when any of these problems are trying to resemble real life situations, it can get wordy. So what I suggest, if you can, kind of draw what's happening. So we're not going to draw it to scale or anything, but I've got one piece of ribbon here, let's say 24, and then 42 is going to be a lot longer than that, right? Almost double kind of thing, and I don't know. I might have made that totally double, but whatever. That's kind of our idea. What's happening there? Now we want to cut each ribbon so that there's an equal number, or sorry, we want to cut them into equal pieces. I can't even read. I'm sorry. We're going to cut them into equal pieces, meaning that they're all, say, 5 centimeters long. They can't be 1, 5, and 1, 4, and 1, 3. So it has to be an even amount. And then we can't have any. Sorry, we can't have any wasted ribbon. So what we're looking to do, we're seeing if we can't chunk this up. And again, I'm just trying to give a visual here of what's going on so that we have an equal amount, an equal length, and then that they're, I'm having trouble talking. I'm so sorry, guys. We're trying to break it up so that we have these strips that are the same length with no wasted ribbon. So you can see here in this, what I'm really looking at is, well, what's the largest number I can divide into both lengths? And if you're thinking, what's the largest number, because that's going to be the length of the ribbon, what's the largest length I can divide in, then we're thinking about a greatest common factor. The other way of doing it is that in a lot of problems, unfortunately, they have a keyword that kind of helps you cheat. And it says, what is the greatest possible length? Because we're looking for the greatest number, the greatest size to divide in. So we know in this question that this will be a GCF. And once we know it's a GCF, then we just get into those steps. So if you forget, we got to find the primes first. So of 24 and 42, so 24, 12 times 2, 12 is 6 times 2, and then I have one more 2. 6 is 2 times 3, and then there's my other prime 2's. 42, 21 and 2. 21 becomes 7 and 3. And then my other 2. So there's my list of primes, or sorry, there are my primes. Now I'm going to make my common factor list. So we'll see that there, I'll use my red. There's a 2 that's common. I see there's a 3 that's common, and then that is it. Oops, I want my blue. So 2 and 3. And then so the GCF part, remember we just have to multiply my list. So 2 times 3 equals 6. So I'm going to save some room here and some writing and some time. And I'm just going to say to you that then the ribbon length that we're looking to cut is 6 centimeters. So what is the greatest possible length of each piece if there's to be no wasted ribbon? 6. If you make them all 6, that's going to kind of maximize the situation. So that's how we apply our GCF. Example 2. Hamburger patties come in packages of 8. Buns come in packages of 6. What is the least number of packages that can be purchased with no patties or buns left over? Okay, so let's go for our understanding first, so we can pick our GCF, LCM, and then we can also look for that shortcut because a lot of these problems have a little keyword that helps us out. So in this first one, the first way of thinking of this understanding, we know at the start here that we'd have, well, we'll have 8 patties if we buy one package. We wouldn't buy one bun, we'll have, well, 6 buns. Well, now we have too many hamburgers, not enough buns. We need 2 more buns. So now, okay, I better buy another bag of buns. Well, now that I have 12 buns, but I don't want anything left over, right? So I only have 8 hamburgers. I got to buy another package there. So now I'm making 16. And you can see how this goes back and forth. So now I'm forced to buy one more bag of buns. That's 18. Well, now that's not enough. 24. And you can see here what I'm doing is I'm making a common, a least common multiple list. And I could keep going. There's 32. What are we counting by here? 24. And we don't have it yet. Or do we have it yet? We do, right? It's 24. So I'm looking for that kind of list. Now, number one, I just answered it for you. But in case it was a question like this where you're noticing, okay, I'm really making a list, if you're making that list, we know then that's a lowest common multiple. Okay, and then we just find the lowest common multiple. And with the list, if you're allowed to use the list, or you have to use prime factors sometimes. So in my assessments, I will say use prime factors if I want the prime factors. And if I don't, often in a question like this, if they're easy numbers, I'm not going to worry about it. I just want the answer. Now, if you wanted me to show you how to do the LCM method, I will real quick. Remember, you could always fast forward the video if you feel like you understand something. So 4 times 2, now that's 2 times 2 times 2. This is 3 times 2. So that's step 1, that was my prime. Step 2, I actually get to make my LCM. So I see that there are 2's and there are 3's being used. The greatest power of 2 would be in this question right here, 2 cubed. The greatest power of 3 would be right here, 3 to the first. So that's 8 times 3, which is 24, and we already showed that with the old school list method right up there. So it says, what is the least number of packages that can be purchased though? So we know there has to be 24 items, buns or patties. So in the end there, what I'm going to do is I know my buns, or sorry, my patties. You can show this different ways. My patties, I get 8 per package, right? But I know I need to have 24 in the end, so that means I'm going to have to buy 3 packages. The buns, I know that there's 6 per package, and in the end, again, I want 24. So then I could go 4 packages. I use multiplication to show it. You could also have divided. Just go 24 divided by 8, you'd get the 3, and 24 divided by 6 to get the 4. But, so the real answer in this question is I'd need 3 bags of patties and 4 bags of buns. And again, I'm going to save that sentence writing it out just to speed us up a little bit. All right, example 3 of 4. What is the side length of the smallest square that could be tiled with rectangles that measure 8 inches by 36 inches? Assume the rectangles cannot be cut. Sketch the squares and rectangles. So the sketching is just to try to help you understand what's going on. So what is the side length of the smallest square that could be tiled? So what they're trying to do in this question, I'll use red, is we're trying to tile a square space. Okay, so what makes a square a square? Well, the fact that it's got equal side lengths. So now, and in this question, where they're using rectangular tiles. So these rectangular tiles, and I don't know, I'm not going to try to answer it this way, but just that we're having, this situation. We have these equal rectangular tiles, and I didn't even draw that equal, but we're trying to fill in this space with these rectangles. Okay, so we're trying to, oh, my pen didn't work there. Sorry, sometimes it'll do that. We're trying to fill these spaces in. So what we're really doing, everybody, is if this is 8 and this is 8 and this is 36 and this is 36, and remember, these aren't, I'm just totally sketching this. This isn't going to be right. But these numbers, 36, let me get a color here, 36 and 36 and 36 is going to have to add up to the same as the 8 and the 8 and the 8 because these two sides are equal side lengths. So if you think about what that would be, we're looking for a lowest common multiple. We're looking for, if we count by 36s, what number would pop up that also would pop up when you're counting by 8s. So that would end up be the length that these side lengths could be. So let's find that LCM. So 8, so that's 2 times 2 times 2, 36, 9 times 4, which is 3 times 3, and then 2 times 2. And then to actually, so again, that was step 1. This is step 2. To find my LCM, I see that there's some 2's. And I see that there's some 3's. So the greatest power of 2 that I see would be right here, because that's 2 to the power of 3. This one's only 2 squared, so 2 to the power of 3 wins out. And then with the 3's, there's only one option, that's 3 squared. So now I actually have the answer. I just got to convert it to like a nicer form. So 2 to the third is 8, 3 squared is 9, 72. So that means we're going to be looking, if I change my color, this side length is going to be 72 inches. So 8 plus 8 plus 8 plus 8 will eventually equal 72, and 36 plus 36 equals 72 right away. So if I redrew this, really it would look kind of like this. It'd kind of have these skinny long tiles all the way through. All right, so that's how we do that third example. Okay, example 4 of 4. What is the side length of the largest square that could be used to tile a rectangle that measures 8 inches by 36 inches? Assume that the squares cannot be cut. Sketch the rectangle in squares. Now I said that kind of funny because in this one I said used like that. What is the side length of the largest square that could be used? Meaning we're now using square tiles and we're looking at a rectangular area. So it's the same, I guess, overall idea. Okay, except now we know the area we want to actually tile. So we know this is 8 and this is 36. And we're wondering about the square. Just what's the smallest square that would work with this? So we're kind of wondering what is the smallest square that's going to divide into this side length, okay, and to this side length, okay. So we're looking for the greatest common factor, the greatest number that'll divide into both 8 and 36 equally. So that is a greatest common factor. And again, and I think I forgot to mention that in the previous one, this says largest. So it says largest, therefore you can use that. You can use GCF. So let's get working on that. So GCF, just so you know what you're thinking here. It's good to identify that. Step 1, your primes. So 2 times 2 times 2, and then 36. So 9 times 4, 3 times 3, and then 2 and 2. And then we second step, we make our list. So before I do that, let's highlight. Okay, so there's a 2 in each group. There's another 2 in each group. And that's it. That's all that's common. So 2 and 2. So step 3, my GCF. And again, you can show this in likely a lot more condensed form than I am. I have a lot of extra stuff here. But 2 times 2, which equals 4. And we're dealing with, I almost said centimeters, we're dealing with inches. So the largest square that we could use would be a 4-inch square. So again, if I go back here and redraw it, it would come right down the middle here because that's going to be 4 inches and 4 inches. And then I'd need 9. And this is not to scale, right? But that's how we'd work with that. There'd be 9 of these going this way. 9 rows, I guess. Oh, columns, I'm trying. That's the word I'm looking for. Anyway, so that's how you use the greatest common factor in the LCM in a question. Sometimes you have to understand and figure out, oh, it's a GCF or that's an LCM. Other times look for keywords. Greatest, largest, that's the GCF. Least, smallest, that'd be LCM. So that's nice, I guess, if you have that easy out sometimes too. All right, if you're having any problems, make sure you talk to your teacher. Otherwise, have a great night. Goodbye.